All right. Well, I will begin with a word of prayer. If I get up here. Dear Father, we thank you for this day. Again, I thank you for these students. Just ask you to bless our work today. Help us to glorify what we do and understand a little more about how to solve systems of differential equations. In the name of my prayer, Lord Jesus. Amen. You guys have any questions before I get into things? Yeah.
So, Trump abolishes the part of it.
Yeah, that was the hope. But I heard some ugly rumor about him, like nominating some person to be in charge of the department, which sounds counter to my hope. So, yeah. What's that? Well, has it been disbanded? I mean, are you giving me false hope? Like, what's this conversation?
A new update, apparently. He was just like going to sign it.
He's going to.
He heard other people talk about it, but he didn't check it himself.
Oh.
There was memes about it, which I think is good enough.
Well, I mean, no. I'm going to need something other than. I need something past memes. I mean, memes are worthwhile. I mean, a meme is worth more than a study for sure. But you know, yeah. I see there are no actual questions, so I'm going to get started. So, let's talk about the complex eigenvector problem, okay? I just want to give you kind of the bird's eye view here. And the solutions. I guess I've been using R here. dr dt is equal to AR. All right, so here's the deal. If lambda equals to alpha plus I beta is a solution of the determinant of A minus lambda I equals to 0, right? And we have that U vector is A plus IB vector, where A and B are real. All right. Then Z vector is equal to e to the lambda tu is a complex solution of, dr dt equals to AR. Unfortunately, or perhaps fortunately, that's not what we want. We want to find a real solution, right? So the way to come to terms with this is to notice that, by the way, if z is equal to x plus iy, right, where x and y are real vectors, then notice that dz dt is equal to dx dt plus I times dy dt. That's how we differentiate a complex valued function of t. We just differentiate the real part and the imaginary part separately like that. And because of this, notice what happens here. We have dz dt. Well, check it out. So dz dt is equal to a times z by the calculus I shared with you guys in the previous class, right? But what does this imply? This implies that dx dt plus I times dy dt is equal to a times z, but a is x plus iy, right? And that, you see, is ax plus I times ay. So this is a complex vector equation. Every complex vector equation gives you a pair of real vector equations. We can equate the real and the imaginary parts of this. See, the only way for this equation to be true is if I have this guy is equal to that guy, for one. And for two, I also need that the imaginary components match up, all right? So I need this guy is equal to that guy. In short, I have that dx dt is ax, and dy dt is equal to ay. So you see, my one complex solution gets me two real solutions. All right? And for this reason, if we're in the context of getting a complex eigenvector, what we have to do is we have to take the complex solution and simply derive the real and the imaginary part of it. Let's do that. So my z here, e to the lambda t times u, right? Where lambda is alpha plus I beta, and u is a plus ib, right? Still that context. Well, this is equal to e to the alpha t cos beta t plus I times the sine of beta t, all right, times a vector plus I times b vector. I'm trying to do this algebra for you guys once, to do it carefully, and then we're going to seal this wisdom into a theorem which we can just use. All right? We're working on finding the template here of how to solve this problem. We will soon not have to keep doing this algebra. We'll just seal it into place as a theorem. So alpha t cos beta t times a vector minus sine beta t times b vector plus I e to the alpha t, let me make it the next line here, plus, oh no, I e to the alpha t sine beta t times the a vector plus cosine beta t times the b vector. All right. So in terms of my previous terminology, you should recognize this business right here is what I was calling x, and this business right here is what I was calling y. Those are separately the real and the imaginary parts of the complex solution. So in this context, we have a theorem. We obtain real solutions. Let's say R1 is e to the alpha t times cos beta t times a vector minus the sine of beta t times the b vector, and also R2, which is e to the alpha t sine of beta t times the a vector plus cosine beta t times the b vector, all right? So that's the theorem to remember here. If we have all this data up here, right? All this data right here, then output, we obtain real solutions, R1 and R2 like that. So anytime we have a complex eigenvalue, we get a pair of real solutions, just like this. So let's look at an example. If there's a question, of course, I'll try to answer it. But yeah, this may make more sense as we look at an actual example. So we'll look at a 3x3 example. We're going to look at 0, 1, 0, 0, 0, 1. And then the third row is 1 minus 1, 1. And we want to solve dr dt equals to AR. All right. Let's try to do it. Oh, man. Oh. So first order of business, we need to calculate the characteristic equation, right? So I got to calculate determinant of a minus lambda I, which here is the determinant of minus lambda 1, 0, 0 minus lambda 1, 1 minus 1, 1 minus lambda. So maybe you guys figure that out while I'm moving the camera here. So my goal is to illustrate how that theorem we just wrote down is put into practice here for this example. If you look at what I did last class, I basically derived the theorem in the context of the example where we had a complex eigenvalue. All right? Which is always an option. I mean, you can always write down the complex solution and extract the real and imaginary part if you like. But I think it's good practice to not have to go through that every time. All right, so I guess I'll just expand across the top row for lack of imagination. Minus lambda times, I've got lambda times lambda minus 1 plus 1. Minus 1 times minus 1. Yeah. Let's see here. So, lambda squared minus lambda plus 1 plus 1. If I haven't made a mistake, let's see here. Which, let's see here, we have minus lambda cubed plus lambda squared minus lambda plus 1, which if you look at that, we can factor out a minus 1. I'm going to factor out a minus to start with, because I do better without having minuses leading, all right? And if you look at this, we can factor out a lambda minus 1 times lambda squared there, and then this is, of course, lambda minus 1, right? So then by factoring, by grouping, we have minus parentheses lambda minus 1 times lambda squared plus 1. All right? So our eigenvalues are lambda 1 equals to 1, and lambda 2 is equal to plus or minus I, right? Now we're just going to use the plus I in time, but let's go ahead and take care of eigenvalue 1, right? That's a real eigenvalue. We just let's take care of it. So we've got lambda 1 equals to 1. I need to find the basis for the null space of a minus I. So I'm looking for a minus I times u1 to be 0. Now a minus I here is minus 1, 1, 0, 0, minus 1, 1, 1, minus 1, 0, times, let's say, UVW equal to 0, 0, 0, right? I guess this is sufficiently ugly that it might be a good thing for me to show you guys row reduction on this one. So if you don't know about row reduction, that's okay, but row reduction is a nice method to solve these kinds of problems. I think you could solve this without row reduction, like I said, but I'll show it to you anyway. So if we take row 3 plus row 1, we get 0, 0, and 0. And then if I take row 1 plus row 2, that gives me all right. So what this all tells me is that this system of equations is interchangeable simply with like minus u plus w equals to 0 and minus v plus w equals to 0. also known as u equals to w and v equals to w. So apparently u equals to v equals to w. In short, a good choice for u1 would simply be 1, 1, 1. Now, you don't have to do the row reduction I just did to see that. I think if you just take a step back and ask yourself the question, what vector can I multiply this box of numbers with such that I get 0 for the dot product of the first row, the second row, and third row? Like which vector, if I take the dot product with these three vectors, can I get 0? Guessing 1, 1, 1 is not outside the realm of possibility, right? I mean, you're like, well, you found the answer, so it's hard to not see it as a guess. You know, to make this discussion better, I should have asked you to guess it before I derived it, right? Unfortunately, I have no ability to turn back time, so we're kind of stuck with it. Sorry. Yet, yeah. Not God, so I can't do that, but it's coming soon. No. It's quantum. It's funny how people always think of our ignorance about quantum mechanics as license to violate classical physics. But anyway, lambda equals to I. So there's your eigenvector for eigenvalue 1. We got that one. Now for eigenvalue I need to look at a minus ii times, let's say, u2 equals to 0. Now that explicitly is minus I, 1, 0, 0, minus I, 1, and 1 minus 1 minus I times u, v, and w equals to 0, 0, 0. I have grown disinterested in row operations at this point. I think we can all agree that oh, what have I done? Yeah, 1 minus I. Yes, 1 minus I. Thank you. Very helpful. I was about to get really confused. Thank you. All right. So how about this? We can just do substitution, basically, right? So the first row gives me that v is equal to iu, right? The first row gives me that v is equal to I times u. You guys see that? Yes, no, maybe so. And the second row gives me that w is equal to I times v, right? But apparently that's I times iu, right? So that's minus u. So supposedly, I have u2 vector is u for u, iu for v, and minus u for w. Now, which row did I not use? I did not use the last row. To double check my calculation, let us make sure that let's double check and see that this actually is consistent with that. All right? So I should see that minus v plus 1 minus I times my w. Oh, I forgot my u. My bad. So u minus v plus 1 minus I times w, that's supposed to be equal to 0. Is it? Let's try it out. So I've got u minus v was I. What have I done? This is a typo, right? Let me fix that. So the u minus iu plus 1 minus I times w, which was minus u. Does this all work out to 0? I've got u minus iu plus iu. Indeed, it works. Woohoo! So I have simultaneously solved all three equations, right? It looks like there's three equations there, right? But there's not really. there's a redundancy, right? Because we didn't find a unique solution, we found infinitely many. That has to happen for the eigenvalue problem, eigenvector problem. So we found, in fact, here, U2, let's put U equals to 1 because we can. So that gives me a 1, an I, and a minus 1, which gives me, check this out, guys, 1, 0, minus 1, plus I times 0, 1, 0. Recognize, for this vector, this is my quote-unquote A vector, the real part of the eigenvector, and this over here, without the I in it, is my B vector. Now that I have identified the real and the imaginary part of my complex eigenvector, now we can go back and use the theorem and we can solve the problem. So let's do it. Let's do it. So the solution to dr dt equals to ar, the general solution here, is we find general solution as follows. R of t is C1. I'll do the real part first. So C1, what was my real eigenvalue? Just 1. So C1 e to the t times my my 1, 1, 1 vector. All right. Then I do plus C2. So, okay, guys, for my complex eigenvalue, you guys tell me, what's alpha, what's beta? Alpha equals to what? Beta equals to what? We have to recognize the patterns, right? Noticing is an important part of mathematics here. So alpha equals to 0, and beta equals to 1, right? So what's e to the alpha 0? E to the alpha is e to the 0. So the exponential terms don't appear. We just get sines and cosines. So we get C2. I'll put some big old parentheses here. I've got myself a cosine t times my A vector. 1, 0, minus 1, right? Minus sine t times my B vector, which in this case is just 0, 1, 0. All right? Plus C3, big parentheses here, sine t times my A vector, plus cosine t times my B vector. And there you go. That is the general vector solution, bless you, to this problem. What system of differential equations have we solved, and what is the scalar solution here? Let's talk about that. Let us unravel the meaning of this calculation we just did, all right? So the original differential equation, we can write it, what is it? Let's explain what we just did. So my original differential equation, if I use, let R be x, y, z, right? For the sake of discussion, we were looking at dx dt equals to blah, dy dt equals to blah, dz dt equals to blah. You guys tell me the blah, blah, and blah from my A. What was it? Working backwards, what system of differential equations do we actually solve here? 0, 1, 0, the top row, right? So we have dx dt equals to y. We had dy dt equals to z. And we had dz dt equal to, this is the interesting one, x minus y plus z, right? So this system has solution I could say scalar solution, if you like. X equal to, apparently, C1 e to the t plus C2 cosine t plus C3 sine t, y equals to c1 e to the t minus c2 sine t plus c3 cosine t. And finally, z equal to c1 e to the t minus c2 cosine t minus c3 sine t. And I mean, I'm sure there are professors out there who dogmatically insist that you write your answer in the form I'm about to put in the blue box. I am not that guy. I do want you to understand that this and that are two different notations for the same solution, right? That's the vector form of the solution. That's the scalar form of the solution. Please understand that going through this complex eigenvalue calculation has allowed us to solve this system of coupled differential equations as we just did, you know, without so much as an integration in sight, right? It's just algebra. It's almost always just algebra in here, isn't it? Until it's not, yeah.
Hypothetically, if the vectors for cosine and sine were the same, then
If the vectors for cosine and sine were the same,
meaning like
impossible.
that's
Impossible. If alpha plus I beta, well, there's one time it could happen. If beta was 0, but we insist that beta is not equal to 0. Beta not being as, if we have a times, let's say, a vector plus ib vector is equal to alpha plus I beta times a plus ib. It is a theorem of linear algebra that the vector a and the vector b are linearly independent. This is a theorem of linear algebra, that the real and the imaginary part of a complex eigenvector are necessarily linearly independent. As such, what you're worried about, namely that a and b are a multiple of each other, thankfully that doesn't happen. That's a good concern to have. Yeah. I won't prove this for you guys. You don't really want to see it. Right? No, it would take me 5 minutes. I'd probably get confused. I've done it before. It's in my linear algebra notes. It's not a special. To see the proof of this, you really need to think about coordinate systems and things, in my opinion, but whatever. It is true. And of course it was true for this example, right? Not an accident. It always happens. So. So that's pretty much it, guys, for like complex eigenvectors. That's the whole song and dance. I mean, I could do another example for you, but you've seen a 2x2 example. You've seen a 3x3 example. I could make up a 4x4 example if you'd like. You know, let's do it. All right, fine. Let's get nuts. Where did I put my eraser?
right behind you. It's a small one.
That doesn't count.
Is it on the camera?
Nice discovery.
Who stole my... Someone stole my eraser. Which one of you did it? All right, I did it to myself, apparently. Just spraying it.
Oh no, the whole head. Oh wow.
This is somewhat inefficient. Like I would be... This is dumb. Not as dumb as using the actual eraser, but it's getting there. All right. What's that? Doesn't work. It just smudges the board. Although, you might say, isn't that what you're doing right now? So, yeah, I guess I see your point. All right, so here's what's going to happen. I'm going to put a problem up here. And then and then what I'm going to do is I'm going to go back and get my eraser, yeah. So example, where are we, 3? Oh, 2, example 2. Suppose we have dx1 dt, dx2 dt, dx3 dt, dx4 dt. All right, and let us suppose that we have 2x1 minus x2. We've got ourselves a handy dandy 9x1 plus 2x2. Double check that. All right. And then we've got minus x4 and x3 down here. All right. Solve it. All right. You guys solve it. I'll give you a minute. I'll be right back. Once we get past this example, I will talk to you guys about the mystery that we couldn't solve last time. Hello. Forgot my eraser. Forgot my eraser. I'm lost without my eraser. You guys solve it? What are the eigenvalues? Oh, come on. All right, fine. You guys gotta pick up the pace, otherwise the next test's gonna, you know. I'm joking, mostly. Let's see here. The determinant should be easy because you should get a block diagonal matrix. So you can just, the determinant of a block diagonal matrix is the product of the determinant of the blocks. So really, this determinant just is a product of two 2x2 determinants, if you look at it, right? Well, here, I'm going to get A equals to 2 minus 1, 9, 2, 0, minus 1, 1, 0. Everything else is 0. So when we look at the determinant of A minus lambda I, we've got the determinant of 2 minus a lambda minus 1, 9, 2 minus lambda, and then down here you got yourself a minus lambda minus 1, 1, like that. Everything else is 0. Fun fact, that's the determinant of these guys. Now, admittedly, if you don't know that, that would have slowed you down, right? but now you know it, so you don't need to be slowed down again. And that's lambda minus 2 quantity squared plus 9, lambda squared plus 1. So lo and behold, lambda is equal to 2 plus or minus 3i, and lambda is equal to plus or minus I. Some of you are still using the quadratic equation. I don't understand why that is. I really don't. But whatever. I can't stop you. But there's a 40% chance you'll be wrong when you use it, so just keep that in mind, right? If we identify this as, lambda minus alpha squared plus beta squared, I can read from this my alpha's 2, my beta's 3, right? That's it. All right, so then those are my eigenvalues, and I think we should just use, the plus, because why not? So if I have lambda equals to 2 plus 3i, I do, a minus parentheses 2 plus 3i times I, that times my u vector equals to 0. All right, so think about how that works out. The 2's, they be canceling, and you just get like a minus 3i here, minus 1, 9, 2 they cancel, and the minus 3i survives. You got that. 0, 0, 0, 0, 0, 0, 0, 0. And then down here, we get, yeah, it's ugly, isn't it? Yeah, thank you. Minus 2, minus 3i, minus 1, 1, minus 2, minus 3i, right? So we've got all this times my, I guess I'll do u1, I don't want to use u1, uvw? Okay, u, v, w, upsilon. No one expects the upsilon. Upsilon's my Greek letter for the day. I'll be working upsilon into the next lecture as well if you want to stay tuned. So, it is upsilon. All right, so here's the thing, guys. You can look at so this is like, yes, it's 4 equations and 4 unknowns, but is it really?
No.
It is not. You have, basically, this boils down to minus 3i minus 1, 9 minus 3i times what? Times uv equals to 0, right? Or minus 2 minus 3i minus 1, 1 minus 2 minus 3i times w upsilon equals to 0. Fun fact, this has non-zero determinant. Don't ask me what the determinant is, but if you look at it, it's pretty obvious it's not 0, right? Because you've got this complex number plus 1. And it's fairly clear that that complex number is not 1 or minus 1, right? So it's fairly evident that the determinant's non-zero. If we have a non-zero determinant times a vector equals to 0, non-zero determinant matrix has an inverse matrix, right? Which means I don't need to like drag this out any longer. This immediately implies that w and upsilon are 0. So there's half the battle done. This over here, these are the same equation twice, right? It's the same equation. It's duplicate. To get from here to here, what do? Multiply by what? Multiply by 3i. That's right, because minus 3i times minus 3i, it be minus 9i squared, also known as number 9, right? So what does that mean? That means we calculated the eigenvalue correctly. Hooray, because these cannot be the same equation, cannot be different equations. If they're different equations, that would mean the determinant of this 2 by 2 matrix is 0 and non-zero, and therefore uv would also be 0. That would be a problem, because then we wouldn't have a non-zero eigenvector, which is, we can't allow that. So good news, we can just focus our attention on like the first one, right? And that tells me what? That tells me minus 3i u minus v equals to 0. V apparently is minus 3iu. Put this all together, we've got our u1 vector, we'll call this 1. u1 vector is, I'm going to put u equal to 1. V is equal to minus 3i. My w is 0, my upsilon is 0. And so that gives us a 1, 0, 0, 0 plus I times 0 minus 3, 0, 0. There's my A vector, and here's my B vector for this guy. S is good. We still got another eigenvalue to do, right? This determinant calculation here is right on the edge of what I think is test reasonable for you guys. It's borderline. I wouldn't want to put 2 of these on the test. And if I did put this on the test, I would be tempted to give a hint. Something like, hey, fun fact, lambda equals to 1 is an eigenvalue for this matrix. See, if I tell you that, that means you can factor out lambda minus 1. All of a sudden, the algebra here becomes much less mysterious, right? So typically, in a 3x3 problem, I give you some kind of information that allows you to not just factor in the dark. Because factoring a cubic, you know, outside of information, it's troublesome. Yes?
Can you explain real quick the reasoning behind the W matrix and how it's like an non-zero determinant, so you know that W has 1 is 0?
Sure. So any matrix which is has a non-zero determinant, that means we can calculate the inverse, right? And if you can calculate the inverse, like just forget about the letters and everything. Let's just think symbolically for a second. I've got a matrix M times a vector, let's say C, right? Equals to 0. If M inverse exists, I multiply this equation by M inverse. But the inverse matrix times 0 is just 0. And the inverse matrix times the matrix gives me the identity matrix, right? They cancel out. The matrix and its inverse cancel out, and you're just left with the constant must be 0. So if a matrix is invertible, and it is invertible if its determinant's non-zero, and we have a homogeneous equation, the only solution to the homogeneous equation is the 0 solution. That's it. So once I know that this is a non-zero determinant matrix, game over, end of story, only the 0 solution. I could belabor it further. I could substitute and solve. We'd still find our way back to 0, but there's no need. So next up, we've got the less scary lambda equals to I solution. And I'm going to look for A minus II times U2 equals to 0. And that is going to give us 2 minus I minus 1, 9, 2 minus I, right? Zeros. And this one's more exciting. Minus I, minus 1, 1, minus I. And U, V, W, upsilon equals to zeros. Same thing we found last time. We're going to find that U and V are both equal to 0, right? Why? Because this matrix right here is invertible, right? Its determinant is not equal to 0. And as such, when I look at the two equations that correspond to the two top rows, which only involve U and V, it's two equations, two unknowns with an invertible matrix. Therefore, only the 0 solution comes out of that. much more interestingly, the last two equations down here, right? We've got ourselves what? We've got, minus I w minus upsilon times, minus upsilon is equal to 0. Or if you like, we could write w minus I times upsilon is equal to 0. Now I certainly don't need to write both, right? These are the same equation. Do you agree? I take this and let's see here. Multiply that by minus I. Wait a minute. Uh-oh. They don't feel like the same. Hold on a second. Huh. Yeah. Okay, so this one, you say this one says IW equals to what?
Negative IW is equal to epsilon.
Upsilon equals to negative IW. Okay, then what?
Just multiply by I, then it's I epsilon is equal to, it'd be
I upsilon equals to minus I squared W, also known as W.
and then for that one you just add I epsilon.
Okay, then move it to the other side. Yeah. Okay, so yeah, good. I just couldn't see it in my head for some reason. All right. This calculation is not needed. This is a redundancy check. If I've calculated the eigenvalue correctly, it should be the case that at least two of the equations are redundant, because I have to have that freedom. I can't have a unique solution to the system that would only leave me the 0 solution. So it must be the case that at least two of the equations are repeated. All right? Okay, so then, excuse me, I'm kind of partial to this one, W equals to I upsilon. So that gives me my U2 vector. I'm going to set upsilon equal to 1. And my U2 vector is then going to be a 0, W equal to I, upsilon equal to 1, which is 0, 0, 0, 1, plus I times 0, 0, 1, 0. This is what I should probably call A2, and this is what I should probably call B2. I really should have labeled these A1 and B1, since in this problem there's more than one A and B, right? So I got my two complex eigenvectors, I got my real part, my imaginary part, and so let's put it all together. What's the general solution? We can just write it down now. We just use the theory, write it down. Let us write down the answer. This is a 4x4 problem. It should have 4 constants in the solution and 4 linearly independent fundamental solutions. Oh, no. All right, so here we go. Thus, R equals to C1. So lambda 1 was what, 2 plus 3i, right? Lambda 2 was I, just to remind myself. So I've got C1 e to the 2t, parentheses, cosine 3t, all right, times my A1 vector, minus sine 3t times my B1 vector, all right, plus C2 e to the 2t, big parentheses here, sine 3t times my A vector, plus cosine 3t times my B vector, close big parentheses, plus C3 parentheses here, cosine t times my a2 vector plus, rather minus, sine t times my b2 vector plus c4 sine t times my a2 vector plus cosine t times my b2 vector. Let me put in the vectors. So my a1 was 1, 0, 0. My my b1 rather, was 0, minus 3. And last but not least, my a2 was 0, 0, 0, 1. And my b2 was 0, 0, 1, 0, and 0, 0, 1, 0. You'll forgive me if I don't write out the scalar solution this time, because I just don't feel like it. Okay, but here you go. This is the vector solution. I don't understand why you guys didn't have this done in the time I was going to get the eraser. I mean, come on. Yeah, you know, just got to pick up the pace.
So I would assume this is not fair for a test, but fair.
Oh, this is totally fair for a test because this is actually easier than my previous example. Don't you think? It really is an easier example because we never faced the 3 by 3 factoring problem. To me, the irreducible complexity of the cubic factoring thing is the hardest thing that we came to today. But I don't know. I mean, this is a nice problem. If I want to kill 2 birds with 1 stone for the test, like, here's what I could do for this problem, is I could make one of them have real eigenvalues. I can make the other one have complex eigenvalues. That way I'm testing real eigenvalues and complex eigenvalues at the same time. Woohoo! But on the flip side of things, I'm then punishing all of those of you who don't understand that the determinant of a product is a product of the determinants for a block diagonal matrix, which may or may not be something I actually have on my list of things to take vengeance over. So, you know, be generous. Be generous with vengeance. No. Okay, let me move on here. So we should talk a little bit more about the theory of all this. And the next bit of theory I wanted to talk to you guys about is a little bit more about solution matrices. What was a fundamental solution matrix? Do you guys remember? What is a fundamental solution matrix? Can you tell me?
What was the question?
What is a fundamental solution matrix for a differential equation, a system of, you know, our differential equation has the form dr dt equals to a times r, let's say, r vector. What do we mean by fundamental solution matrix?
Isn't it all of the R vectors are in the matrix? Like all of the R vectors that...
All of the r vectors. So it has something to do with solutions? I mean, yeah.
And something that's fundamental.
So dr dt equals to AR has matrix, let's say, of functions. I'll use a big X for it. As a so-called solution matrix, if and only if dx dt is equal to ax, all right? The other day, we showed that this means every column of x is a solution to star. I'm going to call this thing star because I'm tired of writing it. All right? To say it's a fundamental solution matrix is one more thing. It's a solution matrix, which is also what? Also has the determinant of x not equal to 0. By the way, that means the columns of x are linearly independent. And if you put that together, what that means is for a fundamental solution matrix, if we take the set of the column solutions, the set of solutions defined by the columns of the matrix, that is itself a fundamental solution set. And remember, the theory of this problem simply says this: if you have a fundamental solution set, we can form a general solution for the problem by taking a linear combination of that fundamental solution set, right? So something I almost assigned to you guys as homework, but I decided against it, was the following theorem. So here's a theorem. If x and big Y are two fundamental solution matrices for star, then x is equal to b times y for some constant invertible matrix B. So like, if we assume that if we assume that x is a fundamental solution matrix, right? If we let yj equal like column j of the fundamental solution matrix Y, then yj has to be equal to, c1 x1 plus plus cn xn, where x1, well, let me just write it this way: x1, x2, xn is the matrix X, right? So like I'm using x1 for the first column in X. So now why is that true? Yj is a solution, right? The jth column of Y is a solution. If it's a solution to the differential equation, it must be that there's some linear combination of the fundamental solution set x1 through xn which builds that solution. And since that's true, this we can rewrite as the matrix X. Well, let me write it. We can rewrite that as the matrix x1, x2, xn times the column vector, like this. In other words, it's x times some column vector, which I'm going to call Cj for the sake of, it has a j dependence here, right? We're finding coefficients to build the jth column in Y, so there's a j dependence. But I can do this for each j, all right? I can do this for each j. So I can do like y1 is x times some constant vector c1, y2 is x times some constant vector c2, and so forth, constant vector cn. And you put that together, this gives us that y1 through yn is equal to x times c1, x times cn, which by the matrix multiplication property, the column by column rule, is really this just the matrix X times C1 Cn. But what this tells us then is that this is Y is equal to X times some matrix B oops. You're not allowed to do that, but I am. There we go. so y, this is y, is x